Good morning, this is Dr. Kumar, Arya, Associate Professor in Department of Chemical Engineering, IIT Jalandhar. Today I am going to explain the fluid flow in a narrow slit. So if we will see the problem statement, problem statement is consider a fluid of density rho in incompressible laminar flow in a plane narrow slit of length L and width W formed by two flat parallel walls that are a distance 2b apart. End effects may be neglected because the distance between the two plate B is very less than the width of the plate and the length of the plate. Fluid flows under the influence of a pressure difference delta P in upward directions or by gravity or by both in downward directions. Three things need to be determined. The first is determine the steady state velocity distribution for a non-Newtonian fluid that is described by Bingham model. Second part, obtain the volumetric flow rate for a Bingham fluid in slit. Third part, obtain the expression for shear stress profile for a Bingham fluid. So if we draw the schematic of the flow, so this you can see that this is actually your top plate and this one is your lower plate. The gap between the two plates is this one, which is we have considered 2b. The center of the origin is being considered in the middle of both the plates, so this is here, and top plate is being considered at b distance apart and bottom plate is minus 2b minus b distance apart, so total gap between the plates is 2b. Direction of the flow is being considered as x and the variation in the velocity is being considered only in y directions, which is the direction of the gap between the plate. Because the width of the plate is significantly large as compared to the gap between the two plates, so maximum variation would be only in y directions as compared to the direction z. There would be no variation in x directions because we have considered the fully doublet flow. So G always act vertically downwards, and this slit we have deliberately considered a theta degree inclined so that we can change it into the any orientation, and the derivation what we will get from here will be applicable in all directions by just changing the theta only. So x1 is the origin of this slit here where the pressure is being considered P1. x2 is the end, which is L distance apart, and there at that particular end is pressure is P2. So flow is going upwards, so it need a applied pressure. So this P1 always greater than P2 in order to make it flow. So this is the width of the plate and this is same. So for this case, if we will apply the momentum balance in the direction of the flow, so this is x momentum balance in rectilinear coordinate. So for this, if we will put a constraint for our condition here, so first thing is this is steady state flow, so this time derivative would be 0. Second constraint we have put here the fully doublet flow in direction x, so velocity should not change with respect to x coordinate, therefore this term is 0. Another constraint we are considering that flow is totally one-dimensional, means no velocity component in y directions, no velocity component in z directions, therefore v and w are 0. In this particular side, the right hand side, this term is non-zero, this is also non-zero. Now this term is again getting 0, that del square u upon del x square due to fully developed flow conditions. Now this del square u upon del z square, the velocity variation, x velocity variation due to z coordinate is not much as compared to this del u upon del y, because delta y is significantly low as compared to delta z. So magnitude wise, del u upon del y term is much more significant as compared to del u upon del z. So del u square upon del square u upon del z square term is also getting cancelled. So finally we will end up with this equation, the 0 equal to minus rho gx minus del p upon del x plus mu del square u upon del x square. Now we can rewrite this by taking this del and mu inside the bracket. So here from this equation from velocity is being converted into in terms of shear stress. Now we can write del tau yx upon del y equal to minus rho gx plus del p upon del x, and this whole term on right hand side being considered delta p dash, or you can say this is modified pressure drop, modified pressure gradient actually, delta p. So this is what you have here. Now this partial derivative from here can be converted to the total derivative, because shear stress is getting changed with respect to y coordinate only, and this equation is valid for all type of fluid actually, Newtonian, non-Newtonian, polymeric. Only thing you have to put the correct expression of shear stress. Now for this case our conditions are, because we have considered origin of the coordinate at the center between the gap of two plates, so at the center the velocity of the flow should be highest, so therefore at that particular time the shear stress must be equal to 0. So if you substitute this actually and integrate this equations, you will get this equation, del tau yx equal to tau yx equal to delta p dash y plus c1, and now you are substituting this condition, y equal to 0, tau yx equal to 0. So from here you are getting c1 equal to 0. So it means your expression for tau yx equal to delta p dash y. So this is the tau yx expression for this problem actually. Now for Bingham fluid, tau yx is given by tau naught plus mu del u upon del y. So to make them flow you need a minimum stress, and that is called critical stress or yield stress, and if your magnitude of your applied stress is less than or equal to this tau naught, then till that particular time the fluid will not flow or the material will not flow. After that it will start flowing. So you need a minimum shear stress, below that it will not flow. So if you put that condition here, so if you have this eta is, you can say, the apparent viscosity. So in that particular point here, this del u upon del y equal to 0 if tau yx is less than equal to tau naught, and for that if we say the eta equal to this, that mu naught plus tau naught plus minus del u upon del y, and here we can write that tau yx equal to minus mu naught del u upon del y plus minus tau naught if tau yx is greater than equal to tau naught. So here we say that till a particular value of the shear stress, if tau yx less than equal to tau naught, there won't be any flow, and therefore this fluid will become just like a solid material, because the apparent viscosity would become infinity, and del u upon del y term would be equal to 0. So in this case, if you write there for Newtonian fluid and mu naught is Bingham parameter models, so if you say here the tau by x equal to minus mu naught del u upon del y plus tau naught, so this is tau y x is positive. If tau y x is the negative, then tau by x equal to minus mu naught del u upon del y minus tau naught. So in this case, there would be the region in the center of two plates where the velocity would remain constant for some particular distance, and after that it will keep on decreasing actually, because you are moving close to the fixed plate which are stationary, therefore velocity will keep on decreasing. So in the inner plug flow region, so this tau by x would be equal to plus minus tau naught, and this is the region for that either you go to the plus b side or minus b side, or this we have considered here, or y naught. So there tau naught equal to delta p dash y naught. In this particular range, your your del u upon del y term would be equal to 0, or the net shear stress would be less than equal to your tau naught, so total applied net stress would be 0. Now let the inner region would start from minus y0 to y and to less than y0, where the shear stress is less than the yield stress. So this is the condition here, minus tau naught less than equal to tau yx less than equal to tau naught. So inner plug flow, the region we are denoting by subscript I. So since tau yx is a finite, so we are putting tau yx equal to eta del u upon del y plus tau naught. So if we solve this, we are getting this minus eta del u upon del y equal to tau yx minus tau naught minus tau yx, and this term is actually 0 because tau yx is less than equal to tau naught, so therefore this whole term is getting 0. So we solve this here, so we are getting del u upon del y equal to 0. If we integrate that, so you are getting the ui equal to c1, means the velocity is constant for the condition here, for this condition, till that your shear stress is less than equal to your tau naught, or minus y0 to y naught. So this is called inner plug flow velocity. Since inner plug flow is constant, so the fluid is in plug flow in inner region only. Now after that, from the region there would be outer regions. So let the outer region would be denoted from y naught to b in positive y side, and minus y naught to minus b in the negative y side. So in this case, so in plus side velocity decreases with increase of y, so you will get del u upon del y less than equal to 0. On the other side, velocity decreases with the decrease in y. So in this case you have minus b less than equal to y less than equal to minus y naught, so del u upon del y is greater than equal to 0. So the shear stress is given by this tau yx equal to tau naught minus mu del u upon del y. So this is in positive y side. This one expression is tau yx is minus tau naught minus mu del u upon del y. This is expression for negative y sides. So we can solve it either of the side, and because the profile the symmetric, so we can make it the full solution from half solution of the problem. So tau yx is given by this expressions as we got previously, delta p dash y. Now from here we can write delta p dash equal to, we can substitute the expression of tau yx from here. Tau yx is tau naught minus mu naught del u upon del y from equation number 1. Now from here we can get the expression for del u upon del y would be equal to tau naught upon mu naught minus delta p dash upon mu naught into y. we can integrate this. So if we integrate this, you will get mu naught equal to tau naught upon mu naught y minus delta p dash 2 mu naught y square plus c2. Now boundary condition we have here that u naught would be equal to 0 at y equal to b in no slip condition, because we will reach to the upper plate which is stationary. So by the substituting this boundary condition into this expression here, so we will get this expression, the 0 equal to tau naught upon mu naught y minus delta p dash 2 mu naught b square plus c2. So if we solve it, we will get expression for c2 would be delta p dash 2 mu naught b square minus tau naught upon mu naught into b. Now we can substitute our constant v2 in this equation here, and we will get expression for outer plug flow velocity is mu naught equal to minus tau naught upon mu naught b bracket 1 minus y upon b bracket close plus delta p dash b square upon 2 mu naught 1 minus y upon b whole square bracket close. So this is for the region y naught is less than equal to y less than equal to b. So to get the velocity profile, we have to get the ui, the inner plug flow, the region velocity. So at the inner plug flow here at y equal to y0, so the velocity at the inner plug flow ui at y0 would be equal to u naught at y0, because it's a continuous fluid. So at y equal to y0, inner plug flow and outer plug flow should have the same velocity. So if we can put here y equal to y naught, and that should be the equal to your velocity of inner plug flow region. So we substitute here y equal to y naught here. So you substitute there y equal to y naught, so you have just here y naught upon b. So delta p dash b square upon 2 mu naught 1 minus y naught upon b whole square. Now these are the expression for tau yx equal to delta p dash y and tau naught equal to delta p dash y naught actually. So if we arrange that, take the common, and then finally we are ending here the u naught at y equal to y0 is delta p dash b square upon 2 mu naught bracket 1 minus y naught upon b whole square. So this is the velocity for inner plug flow, the region here ui equal to delta p dash b square upon 2 mu naught 1 minus y naught upon b whole square, where here the by this is applicable here for y is less than equal to y naught, and for that this velocity is constant, is not the function of y. Now the u naught velocity is given by this expressions here, that delta p dash u dash y dash here. So this is practically here is y actually, this is y upon b whole square. So this is the outer plug flow velocity, therefore velocity profile is flat in the inner region because it is not variable, and for outer region it is getting changed. So this is the velocity for outer plug flow actually, minus tau naught upon mu naught b 1 minus y upon b delta p dash b square 2 mu naught and 1 minus y upon b whole square. So in that case if you draw the velocity profile, so velocity profile will this is in the center region here, so you have the flat velocity profile here, so this is called inner plug. After that there is the parabolic profile here. So in this case the fluid will behave as a Newtonian fluids here. So this flat region is only because of this inherent property of the Bingham fluids. So this is complete profile. Now this profile can also be generated alternatively by this way, that this you have already del upon del tau x yx upon del y equal to delta p dash. This can be integrated this way. So you have a constant at y equal to 0, tau yx equal to 0, because this is far away from the boundaries, and the velocity would be higher here, maximum. So maximum condition we can force the shear stress must be 0. So therefore this constant c1 equal to 0. So you have tau yx equal to delta p dash y. Now this is for equation 1. But for Bingham model we have tau yx equal to tau naught mu del u upon del y. So this we are considering a two region here. One is that y equal to y is less than equal to y0, so minus y0 y and y0, and tau yx is less than equal to tau naught. So therefore in this particular range tau yx minus tau naught would be always less than equal to 0. So it should have a finite value. So to make it finite we are making it 0 here. So if we will integrate that to c1 equal to c2, so this is the inner plug flow region here. Velocity is constant for this range at y is less than equal to y0 or y is less than equal to minus y0. Now for outer plug flow part we are considering from y0 to b or minus y0 to minus b. In that particular part this equation is valid. Tau yx equal to delta p dash y from equation 1. Now we can substitute the expression for tau yx. From here we can write the expression for del u upon del y would be equal to minus tau naught upon mu plus delta p dash y upon mu. This can be integrated here. So upon integration we will get this this equation actually, u naught minus tau naught upon mu by plus delta p dash y square upon 2 mu plus c3. So we have to find this constant c3. So we have boundary condition at y equal to b, u equal to 0, that upper plate, so it is no slip condition. Y equal to minus b, u is again equal to 0, so this is the lower plate, so again no slip condition. So by substituting the first condition there, so we can find here 0 equal to this. From here we can find c3 expression is tau naught b upon mu minus delta p dash b square upon 2 mu. So we can substitute back in equation number 3. So we'll get the expression for velocity would be by the substituting there. So this is the constant, this is the previous expression of that. So you will get expression for mu naught, that outside velocity u naught equal to tau naught b upon mu 1 minus y upon b minus delta p dash b square upon 2 mu bracket 1 minus y square upon b square. So this is the expression for outer plug flow velocity. So at y equal to 0, the inner plug flow and outer plug flow should have same velocity. So if you just put y equal to 0 here, you will get this expression that ui0 would be ui naught equal to tau naught b upon mu 1 minus y naught upon b minus delta p dash b square upon 2 mu minus y square upon b square. So now we have tau yx is given by this expression delta p dash, so we can find tau naught corresponding to y naught. Now we can change delta p dash actually here, so you can change the expression for tau naught from here. So we can change the tau naught here. At the place of tau naught we have substituted delta p dash y naught here. This side no change, so we are writing here all this equation in terms of pressure gradient only, or delta p. So if we can take the common here, arrange it, this equation actually. So if we arrange that, simplify it, so we will get expression for ui not equal to u not equal to minus delta p dash b square upon 2 mu 1 minus y naught upon b whole square. So this would be the expression for inner plug flow velocity, which is constant in given range. Now next part is how to find the volumetric flow rate. So volumetric flow rate, you have velocity expression u multiplied by dA, integrate it over the entire area for flow, you will get the volumetric flow rate. So we can integrate minus b to b and 0 to w, and then you have here u du d by dz actually. So d by dz is the difference area. So this is the symmetric flow, so you can have it 0 to b actually 2w here. So width of the plate is always constant, so dz would be equal to w, and this minus b will change to 0 to b by putting a factor 2 here. So we have the expression here u and dy, the profile, the symmetric. So in this case we are considering u as a first function and dy as a second function. So if we say the integration by parts, so you have this uy 0 to b the limit, and then the second part is 0 to b y del u upon del y into dy. So in this case, if we substitute the limit here, so if we substitute here the limit at u at b multiplied by b minus u at 0 y at y0, and then minus this second term here 0 to b by del u upon del y into dy. So this, if you say that at y equal to b, that velocity equal to 0, this is the no slip conditions. At y equal to 0, the velocity is the maximum because it's far from the boundaries, but y is equal to 0, therefore this total product is 0. So this product and this product, both terms are the 0, so we are left with only this term. So the expression for q is now is minus 2w 0 to b by del u upon del y into dy. So this now we can substitute the expression here, tau by x equal to delta p dash y, and we can calculate the shear stress corresponding to distance b at the plate actually. So this is tau b actually, so x can be the removed here actually, or we can keep it x delta p dash b. So from here we can find the ratios of the two, so tau by x upon tau b equal to y upon b. So we can find the expression of tau by x in terms of maximum value of shear stress, that is y upon b into tau b. So from here we can find the derivative of tau by x upon del y, del tau by x upon del y equal to tau b upon tau b upon b. So we will get del y expression is b upon tau b multiplied by del tau by x. So we can substitute this into equation number 5. So equation number 5 was this here. So this here you are this is the term you already have, tau by x upon delta by is the term for y. This you already have del u upon del y. This is the expression for del y. So del y you have now here. So this if you will simplify this, you will get minus 2w 0 to tau b, tau by x upon tau b upon b del u upon del y, b upon tau b del tau by x. So this we have here. Now this again we can arrange here. We have del tau by x, del u upon del y del tau yx. Now we can use this expression again, that del tau by x equal to tau naught plus mu del u upon del y. So from here we will get expression here, del tau yx minus del naught tau naught upon mu equal to del u upon del y. So del y here, del u upon del y expression can be substituted at this particular place here, this one. So for substituting here, you will get q equal to minus 2w b square upon tau b square 0 to b tau yx minus tau naught upon mu del tau yx. Now here again we can break the limit into lower plug flow and upper plug flow part. So there is one range from 0 to tau naught. So this is for inner plug flow. Then we have the another zone here from tau naught to tau b, and these functions are same. We already have it here. So this will help us actually in the sense that in 0 to tau b this velocity gradient is not there, so velocity profile is flat there. So this particular derivative would be 0. So therefore this term would be cancelled out. So we left with only this particular term here. So we left with this term here. So q equal to minus 2 w b square upon tau b square. This the integration term is tau naught to tau b tau by x del u upon del y d tau by x here. So here we can substitute the expression for del u upon del y here in terms of shear stress. This is tau by x minus tau naught upon mu d tau by x. Now this actually you have this term and this can be integrated. So if you integrate that, you will get this tau by x cube upon 3 minus tau naught tau square yx upon 2 tau naught to tau b. And now this can be integrated by substituting both the limits here. So if we arrange them here, so you will get one term here, another term here, this term. Simplify it here, arrange it here properly, and finally you can substitute at last at tau b equal to delta p dash b. You know that. So this is in terms of tau naught here. So the expression here is minus 2w b cube upon mu naught delta p dash 1 upon 3 minus 1 upon 2 tau naught upon tau b plus 1 upon 6 tau naught upon tau b cube. So this is one of the expression for volumetric flow rate. Now if you want to change for Newtonian fluids, so tau naught would be substituted equal to 0. So this term would cancel out, this term will cancel out, and mu naught would be mu. So you will end up with this term. So this is the expression for Newtonian fluid actually, and where delta p dash is given by this minus rho gx del p upon del x. Okay. So this is all about the derivation of the volumetric flow rate in case of Bingham fluid flowing through a plain narrow slit. Thank you.